If you want to understand the motion of anything in orbit around something, you've got to know Kepler's laws. Hi, I'm Dan Roy. With my wife Rebecca here, we used to show the night sky to kids of all ages, but now we've gone virtual. By the end of this talk, you'll be able to appreciate the beautiful minuet of the four major moons of Jupiter and compute their orbits, thanks to Kepler's laws. But first, it helps to remember that Kepler lived during the Renaissance. That's when the West rediscovered the ancient Greeks and their achievements in the arts, philosophy, and the sciences. This is Aristarchus of Samos, for instance, born in 310 BCE, 10 years after the death of Aristotle. Aristarchus is credited with the invention of the heliocentric model. Unfortunately, his successor here, Claudius Ptolemus, Ptolemy to his friends, born in 100 AD, never got the memo. Following Aristotle, he put together an Earth-centric model that endured for 14 centuries. That's until Nicolas Copernicus here, born in 1473, put together his heliocentric model without ever knowing that he had been scooped by Aristarchus 17 centuries earlier. But Copernicus sure knew that publishing these ideas could be hazardous to his health, so he kept his model pretty much to himself. Note that although the Copernicus model on the right was a revolutionary improvement, it still kept the planets in circular orbits. Aristotle again. Copernicus finally published his book on the revolutions of the celestial spheres shortly before his death, in 1543, and he even dedicated it to Pope Paul III for good measure. The printing press had been invented a century earlier, so his book reached quite a few educated people, such as Tycho Brahe here, born in 1526, a very meticulous observer. With nothing but glorified protractors, and the help of his sister Sophie, by the way, he collected years of data about the position of the planets with an accuracy of 1 arc-minute. It is this precise data that allowed Kepler here, born in 1571, to formulate his laws. Fleeing Germany, after he refused to convert to Catholicism, Kepler settled in Prague in 1600 and went to work as an assistant to Tycho, who had the good taste of dying the next year, leaving Kepler with a treasure trove of pristine data. Galileo, a contemporary of Kepler, was born in 1564. Pointing his crude 1-inch telescope at Jupiter, he discovered what we now call the Galilean satellites, Io, Europa, Ganymede, and Callisto. By seeing them orbit the big planet night after night, and seeing that Venus had phases like our moon, he concluded that Copernicus had been right. Of course, these became hazardous to his health. But the Copernicus model, the data of Brahe, the observations of Galileo, and even Kepler's laws were just all empirical stuff. It would take another century. It would take Isaac Newton to make Kepler rules part of the laws of nature. So, what are those Kepler's laws? I'm glad you asked. By confronting his dearest illusion, and thanks to the accurate data of Brahe, Kepler was able to show that the orbits of the planets are not circular, they are elliptic, that their speed cannot be constant but it is periodic and can be predicted, and that there is a mathematical relationship between the planetary orbital period and the semi-major axis of its elliptical orbit. Now, his laws, now validated by Newton physics, are used every day by astronomers and flight dynamics engineers the world over. Okay, so everything moves in ellipses. Want to draw one? Prepare a string of length a plus b. Stick n at 2 points called the foci of the ellipse. Put your pencil in tension. Move around. You got an ellipse. Now, an ellipse is characterized by 3 numbers. Its semi-major axis, its semi-minor axis, and its eccentricity, which, by the way, can be computed from the semi-major axis and the semi-minor axis by using Pythagoras' theorem, by the way. All right, So planets move in ellipses. How eccentric are they? Well, not very much actually. If you look at the data, the eccentricity of Mercury at 20% here gets the cake, followed by Mars. But the orbit of Venus and even the Earth are basically circular, and when you look at the solar system from higher up, you can see that it's pretty hard to tell. Yeah, you can tell Mars and Mercury. But if you put those systems in motion, I want you to pay attention here to the planet Mercury in particular. And here I will play the symphony, The Planets by Gustav Holst, completed in 1960, the Mercury movement, of course. Look at the planet Mercury. Here it is an aphelion. And it is going toward perihelion here. Yep. Did you see it accelerate? Welcome to the second law. The second law says that the area swept by the planet in its orbit are equal in equal amount of time. So A1 is equal to A2 here. So when Mercury is at perihelion here, it sweeps the same area as it does at aphelion there, which means that it's got to be much faster here than it is going there. That is the second law of Kepler. But there is an interesting consequence of this law that is worth diving into. And here we are in polar coordinates. In the dt interval, the theta angle has increased d theta, and the area swept by the planet, the area of the white triangle here, is r multiplied by r d theta divided by 2. So, the area swept by the planet in the delta t interval of time is half of r squared d theta, and Kepler showed that this is constant, no matter where the planet is in its orbit. Now this is huge, because if this is constant, it means that d theta on dt is inversely proportional to the square of the distance between the planet and the Sun. Now Newton will make good use of that later. And although Kepler never knew it, this variation in speed is due to the conservation of angular momentum. Think of the ice skater pulling her arms above her head. She reduces r square. So she's got to increase d theta and dt. She speeds faster. When it comes to the Earth, the ratio between its fastest to slowest speed reduces to 16/15. Chance has it, it's the same ratio as between two half tones in an octave in music. The difference between the notes fa and mi, for instance. So, ever the jovial optimist and life of the party, Kepler concluded, and I quote, "The earth sings mi, fa, mi. You may infer even from the syllables that in this, our wretched home, misery and famine hold sway." Point marrant celui-là. Still with me? Hold on, one more to go. The Kepler third law says that the square of the orbital period is proportional to the cube of the semi-major axis of the orbit. Here are the data for the planets that Kepler knew about. The SMA are in astronomical unit. What's that? I'm glad you asked. An astronomical unit is the average distance between the Earth and the Sun, and it's about 150 million kilometers. And if you look at the crunch numbers now, the cube of the SMA and the square of the period, I think you will agree that it's close enough for student homework. Now, this third law, believe it or not, can be easily demonstrated by using Newton. Let's assume that the orbit is circular. Oh, that will make Aristotle and a lot of old ghosts very happy here. But the blue planet of mass little m here is orbiting its yellow star of mass big M there at a distance that is constant, r, circular orbit, and at a constant tangential speed, v here. I tell you, circular orbits are awesome, okay? So, the planet is subjective to a centrifugal force mv squared divided by r, as well as Newton himself, which is product of the masses divided by r squared multiplied by a gravitational constant here. Now, v is equal to the circumference of the orbit divided by the period p, okay? And when you put this equation here, v equal 2 pi r divided by p, into this, you get that. And by rearranging, you can indeed see that the cube of the distance from the Sun is proportional to the square of the period in its orbit. Ain't that cool or what? It's so simple. Now, Kepler left us with quite a legacy, and it is fitting that the satellite dedicated to the discovery of exoplanets be named Kepler, since it is by measuring the orbital period that you can know the semi-major axis of the exoplanet around their star. And that's important to determine whether they are in the habitable zone or not, which is defined as the place in its orbit where liquid water can exist, because if there is water around here, there is life. Okay? Now, Kepler is dead, however, so long live TESS, the transiting exoplanet survey satellite, will survey 200,000 of the brightest stars near the Sun to search for transiting exoplanets like Kepler did. Test launched in April 2018 on the Falcon 9. Kepler's legacy lives on. Now, here is an extra assignment for credit. Walk in the footsteps of Galileo by observing Jupiter for a couple of months or so. Carefully note the position of the Galilean satellites night after night, as he did, and note their orbital period. Or you can cheat and use a planetarium software like the freeware Stellarium here, which I highly recommend, by the way. Stellarium is free, the price is right. Check the date and time at the top of the display in Stellarium, and you will see that Io takes 1.75 days per orbit, Europa takes 3.5 days, and Ganymede 7 days, the three inner moons of Jupiter and in what is called resonant orbits. Only Callisto bucks the trend, with an orbital period of 16.7 days. And the music you were hearing, by the way, was the Jupiter movement of the same Gustav Holst symphony, The Planets. Still with me? I can't believe it. Well then, by using Kepler's third law, and knowing that the Earth takes 365 days to orbit the Sun, with an SMA of 150 million kilometers, you'll be able to calculate the semi-major axis SMA for all the Galilean satellites. So go ahead, make a spread, crunch the numbers, and check how close you got. In summary, Kepler was able to show that the planets revolve around the Sun in elliptical orbit. They sweep an equal area in an equal amount of time. Their orbital angular speed is inversely proportional to the square of the distance to the Sun, and the square of their orbital period is proportional to the cube of the semi-major axis of their orbit. Here, these are the three laws of Kepler. So, keep learning. Thanks for watching, and welcome to astronomy.